Hey, this is a great question. So I can see that you already kind of figured out the derivative of this, so we won't go through that. We just need to figure out the tangent lines, and that's important to notice. There's talking about plural lines. There might be multiple lines to the curve that are parallel to that line. So how will we do this? First off, I think it would be helpful to kind of visualize the situation. So let me share that real quick. So this is basically a visual of what we're looking at here. And you can see that, the red line here is the curve we're actually dealing with. And then the green line here is the equation they want the tangent lines that we find to be parallel to. And then I've programmed it so that as we move this slider, it will basically show you the equation of the tangent line at a certain point. So I don't know what the exact answer is yet, but it looks like one of our tangent lines, and you can kind of see this, it starts off flat as we go to negative infinity, but here it seems about parallel, more or less, at -3. So that seems like it's going to be an answer. We'll see if that turns out to be true. And then it goes up, and then it kind of pops out on the other side of the vertical asymptote. And then it looks like at 1, more or less, and maybe a little less than that, actually. Maybe something like that, about 1. Yeah, let's say 1 is where the second parallel line is, and then it goes flat again after that. So as you look through this, it seems like when x is equal to 1 and x is equal to -3 is where we're actually parallel to those. But we need to prove that by hand. So let's kind of go through that now. So the first thing I would do here, you've already figured this out. The first thing to notice is that this is the slope, right? The derivative is a function that tells you the slope at every point. So we have a function that tells us the slope at every point. Now, what we need it to be parallel to is this line. So it would be useful to turn this into slope-intercept form, I'll say, to make it clear what the slope of this line actually is. So if I do that, hopefully it's clear that I'll just do that algebraically. Add 2y to both sides, subtract 4 to one side, so x minus 4, then divide by 2. We get x is equal to 1/2. So then divide by 2. -1/2 x minus 2. And if you actually look at our animation, that makes sense, right? Slope intercept of -2, or intercept of -2, y-intercept of -2, and then it looks like the slope of up 1 over 2. So that checks out. So now, what do we do with that? Basically, we need to set it equal to this. So if you set it equal to this, it's a little bit complex. So over x plus 1 squared, right? Because we're saying we need to find the spots, or we need to find the spots on this curve where the derivative, or where we need to find the spots on this curve that are parallel, where the tangent line is parallel to this curve. And then here you'll notice that the slope is 1/2, right? So that's the slope. Parallel means same slope. So you basically set your derivative equation here equal to the slope that you want to force it to be parallel, which is 1/2. And then if we work through this, I'll work through this a bit. You get 4 is equal to x plus 1 squared if you cross multiply. And then we get x squared plus 2x plus 1 is equal to 4. Subtract 4 from both sides. So you get 0 equals x squared plus 2x minus 3. And then see if you can factor, which it looks like we can if we do x minus 1 and then x plus 3 equals 0. So that's how we get the two things that we did see before. We saw that x equals 1 and 3 would be solutions to this, and you can plug those in to just double check them, right? So if I plug in 3 here, -3 I meant. So if I plug in 1, I would get 2 over 2 squared, which is 1/2. And then if I plug in -3, I would get 2 over -2 squared, which is also 1/2. So that checks out. But remember, they're not just asking for the x values, like where the lines are parallel. They're actually asking for the equations of the tangent line. And for that, you would need point slope form. So remember, we already know that, and I won't go through point slope form here, but for the first case, because I only have a couple seconds left, but we know that the slope is going to be 1/2. And then we know that we'll have x minus the x coordinate of the point. And then here, in order to get this, you would basically plug it into the original equation. So you get plus 0. So that should be one of the equations. Hopefully that makes sense, where you can plug in the values. And I'll set them on the Desmos animation. I'll link them below so that you can actually check these results. But the second one should be, let's see, 1/2, and then it'll be x plus 3. And then if we plug in -3 here, we get -3 minus 1, -4 over -2 should be +2.